opening up the booklet, and we're going to start with the brief introduction telling us what we'll cover in this unit. We're going to look at electrolytic cells, and so our terminology, it's really important that we understand what these words mean and that they're talking about different things. So we've had, up until now, electrochemical cells, and now we're going to have electrolytic cells. Okay, so they're two different things. We're going to look at electrolysis reactions and the differences between the two of these, and also how we can use the electrochemical series to predict the products of electrolysis reactions. And we're also going to do a new calculation using Faraday's law. So this is a new kind of calculation that you haven't done before. Now if we look at the introduction on page 5, it's just asking us to reflect on electrochemical cells and corrosion and also redox. All of those reactions were spontaneous. Okay, so as long as we had a stronger oxidizer higher than the corresponding stronger reducer on our electrochemical series, then a spontaneous redox reaction occurred. And that's something, electro. That's a feature of electrochemical cells. Now, for our electrolytic cell, which involves electrolysis, it's not spontaneous. Okay, we have to add electrical energy for it to go. And anybody who uses a like my Fitbit or your phone or anything else that has a battery or a cell in it that's running it, that will be using this technology in that, what do you do when your phone charge level is low? You recharge it. And so when you're using your phone, this is the process that's happening here. It's a spontaneous chemical reaction that is then, we know that we can use that energy. But when our batteries getting flat, then we plug it in and we reverse the reaction by adding energy. Okay, so we're doing this sort of thing all the time. And we've got this little diagram down the bottom of page 5 showing us how these electrochemical cells and electrolytic cells are related. So the electrochemical cell is using chemical energy, but the electrolytic cell is using electrical energy. And there's a summary on page 6, and this is an important summary, so for those of you who like to highlight things, you might like to make a note of this page just to make sure that when you're revising the unit, you come back and, yes, all of this makes sense, and I could, I'm confident that I know what is in this table. So as I said, this is spontaneous. This is not spontaneous. This releases electrical energy from our chemical reaction. Okay, so this is in the table, and this requires energy, electrical energy. And the analogy is that this is like rolling down the hill. You know, like if you're at the top of the hill and you've got a watermelon that you want to pass on to someone that's down the bottom of the hill, it's easy, you just sort of give it a little bit of a push and off it goes. Whereas if the person down the bottom of the hill wants to give that watermelon to the person at the top of the hill, then that's a bit more effort. You've got to keep, probably not a watermelon, but how about we've got to push something up a hill. If you stop pushing, it stops moving. Yeah? So if you let the watermelon start rolling, it will just keep rolling by itself, down, down, down till it gets to the bottom. But if we want to move, and I don't know, have you seen those people, I forget which country it is, but they roll cheese wheels down hills. Yeah? Actually looks like a very dangerous sport. But once those cheese wheels start rolling, I tell you what, you're going to find it hard to stop. Whereas this will, if you stop adding electrical energy, this reaction will stop. Okay? The moment you stop adding the energy, this will stop. And so this one has a voltage greater than 0 because it's releasing energy. This one has a voltage less than 0 because it requires energy. So if we're calculating the energy required from the electrochemical series, you would find that it's a negative value. Yeah, and so that's telling you that you are adding it. You have to add that much for it to proceed. Alrighty. And our first application of electrolysis is electroplating. If you look on page 7, we can see that what we can do here is use electroplating. We'll discuss exactly what we mean there in more detail in a moment. But we can apply a thin layer of a metal to the outside of an object. And it might be to enhance its appearance. It can be also to protect the metal underneath. So for jewellery, for example, you might buy plated jewellery. You know, it might be gold. It might say gold-plated earrings or something like that, which just means that there's been a thin layer of gold applied to the outside to make it look nice, but it's constructed of a different metal. And often those ones will tell you whether there's nickel in there or not, because people can commonly have nickel allergies. Some people say, oh, I can only wear silver jewellery, or I can only wear pure gold jewellery because I react to these other metals. And so the other thing is, if it's only a thin layer, it can wear off, and then you're exposed to that base metal. Could be plated knives and forks, cutlery. You know, if you look at antique cutlery, etc., then if you find a solid silver cutlery set, you'll feel that they really feel heavy in the hand. But you can get cheaper versions where it's just plated with silver or gold, and so they look shiny and nice. But it wears off really easily. If you get a scratch on it, then it may not look so. You'll be able to see the other metal underneath. All right. We also use electrolysis to extract reactive metals from their ores. And probably for us, the most important one is aluminium extraction at Bell Bay. And so Bell Bay at the mouth of the Tamar uses a very significant percentage of the electricity produced in Tasmania, because this reaction to extract the aluminium from the ore requires a lot of electrical energy. The ore comes from northern Queensland, Weipa, and is brought down to Tasmania, and there it's processed. We'll look at a little bit more at that, as I said, later on. Anodizing. Now all of you with phones, if you look at the case, it's probably anodized aluminium. And in this anodizing process, what we're doing is we're making the oxide layer thicker, and we'll talk a little bit more about that as we go on. And by making it thicker, it provides more protection to the metal underneath, and they can also add colour, and like make it look pretty. And we've already talked about recharging of batteries, etc. And electro-refining, so not just extraction, but increasing the purity levels of different metals. So one that springs to mind here would be copper. Copper electrorefining is an important process. Now, if you look at the diagram, or that little teapot diagram down the bottom of page 7, you can see that the object that we are electroplating is the cathode. Now, this process won't work unless our object can conduct electricity. So it has to be a metal or a conductor. For example, it could be graphite, a carbon conductor. But if we wanted to silver plate this teapot, then it needs to go in and be the cathode. Because when we've talked about our, when we've had our redox reactions happening already, it's the cathode that gets built up, isn't it? So it's the same thing happening here. So we're going to be using up the anode and taking the metal from it to apply that layer to the object that is the cathode. So if we look over at the next page, where we're going to start looking in a little bit more detail of what's going on. And so far, a lot of these things have been the same. So why is electrolysis different?